Alrighty, so now microphone, and then we can start. So good morning again, and welcome to another exciting and intense day. I've put on the schedule that I designed before coming here, and we're a little bit behind schedule, which is not a problem because I've planned to have lots of buffer time, right? So we have 3 more full days. So I might actually take off earlier on Friday because my plane is leaving quite late, but I know traffic in Ho Chi Minh City. And if you leave for Ho Chi Minh City at 4, it'll take hours and hours and hours to get to the airport. And that's something I'd rather avoid. No, anyway, now today is a full day, that's for sure. I might extend the lunch break a little bit because I have to pay my bill for the apartment. And the lady who said I can do it with her said she comes at 9 and leaves at 4. And I say, look, I've this 1 hour to get to your place, and would that be fine between 12 and 1? So I'll do that today, because I don't want to run away without paying my apartment. Anyway, so that's for sure. Okay, so that's a little bit of organizational information. Now, let me do something, now yesterday in the afternoon, we did this problem set, and we haven't finished it yet, and we'll finish it today. And I realized that you have had some exposure to panel data econometrics, random effects, fixed effects, yes. But it's not very present. So let me do something I didn't plan to do. This will be a bit taxing in terms of time, but I think it's useful. Let me borrow from another teaching that I do and give you a brief refresher on panel data econometrics, right? So as I said, I'm teaching at the Study Center Gürtensee. Gürtensee is a beautiful place in Switzerland where the Swiss National Bank invites people working in central banks at different countries, literally from A to Z. We even had a central banker from Afghanistan. Now we don't have any more for obvious reasons. I don't know whether there's any Afghanistan central bank anymore, but they did have one. And we have people from Zimbabwe. We did have people from Vietnam in the past. This year we had a person from Cambodia and a person from Thailand. So I'm teaching these courses, and it's super interesting because you are in touch with people who are actually involved in practical monetary policy. So I learn a lot from them because they tell me, look, this is how things work in our country, it's super inspiring. Now the goal of these courses have 2 parts. The first part is to bring people at the same level, because some of the people working in central banks, they have a background in economics, some have a background in accounting, some have a background in finance. So everyone is a specialist in his or her own field, but what you need is kind of an overview, a bird's eye view, and that's my task. Also, what I do is I do a little bit of econometrics, and in a very, say, non-formal way, because it's not, these are people, practitioners, but on the other hand, they are confronted with these methods, right? Suppose you are working in a policy-oriented department, and you have to write reports, and then someone comes up and says, okay, we've run this regression, we've used fixed effects, it's a panel data set, fixed effects, ... clustered standard errors, and if you don't know what this person is talking about, you have no possibility to challenge this person on what he or she has done. So, good. So let me spend half an hour on this panel data thing, because I think it's very useful for doing the rest of the problem set. Okay? Good. So, what is the key problem that we have in econometrics? Well, it's that our estimates are biased. When we run regressions, we get biased estimates. And that's often due to what we call omitted variable bias. So we have a variable that matters, but we don't include it in the regression. It's as a consequence in the error term, and if this variable is correlated with one of the regressors that we have in the regression, then we violate the most important condition, which is EXI epsilon I equals 0, right? So that's, So that's the point. Now, suppose you're running this regression, right? Regression, some variable yi on a bunch of potential determinants. Now, however, the correct model has this ci in there. Ci is what we call an unobserved effect. Suppose there's something that is special about the observational unit I that you cannot observe. But it's there. Now, here are two examples. Suppose you are running a wage regression. So you have a person's income on the left-hand side, and you have all kinds of things on the right-hand side. For example, the amount of schooling that a person experienced. So regressing a person's income on the person's education. And suppose that you get a highly significant coefficient, a positive one, right? Suggesting that people having more schooling get higher wages, which sounds reasonable. Now, the problem is there is something that you might not be able to observe, namely the person's ability or talent. Now, ability might be correlated with schooling. So people who are able to, understand things, who are able to process information, they might enjoy going to school. Other people might not enjoy going to school and university, right? So now the problem is that it might be actually ability driving higher wages. So people who have higher ability, they get higher wages, and they also have spent more time in school. So it's not the schooling as such, it's the ability that's driving the thing. And the coefficient of schooling is just biased. It suggests an effect of schooling on wages, but in fact it's the ability. But the ability is not in your regression because you cannot observe it. The second problem is, suppose that you regress a country's economic growth on the investment share. So we have good reason to believe, the Solow model, that countries investing more have higher growth rates. Now, maybe growth is not driven by investment, but growth is driven by institutional quality, absence of corruption, security of property rights. And the quality of institutions is correlated with investment. So it's not that countries who invest more grow faster, it's countries who have better institutions grow faster, and they also happen to invest more. So this is our two typical cases of unobserved heterogeneity. And the problem, I already spilled the beans. If CI varies across observational entity, it gives rise to unobserved heterogeneity. So if something that you cannot observe. Now, can we estimate the parameters of interest consistently by OLS if there is unobserved heterogeneity? The answer is yes, if, and I'm now coming to the point, if the covariance between the unobserved effect and any of the regressors is 0. So it's not correlated. However, no, if this covariance is different from 0. So we have something that we don't observe, and it's correlated with a variable that we have in the regression. And then, as a consequence, we are getting biased estimates. And that's probably the worst thing that we can get, because it suggests a relationship that is actually not there, or it suggests a positive relationship while the true relationship is negative, all those problems. So it's a typical case of emitted variable bias. So examples of correlated unobserved effects, I said I spilled the beans, ability affecting both education choice and wage, or institutional characteristics affecting both investment rate and growth, right? So you have the investment rate in the regression. You do not control for institution characteristics because you can't. I mean, there's a way by now we can measure institutional quality, but suppose you cannot measure everything that matters. Suppose you cannot, in a wage regression, you cannot measure a person's ability. So it might be that, in fact, the positive effect of education on wages is just picking up the positive effect of ability. So Unobserved heterogeneity is especially important in cross-country analysis, by the way, because, I mean, individuals are different, but countries are super different, right? So you have a lot of stuff, a lot of dimensions along which Vietnam differs from Germany, right? So you can of course control for a lot of stuff, but you cannot control for everything. Now, using panel data, and that's the big issue here, using panel data offers a solution to the problem. That's the point, right? Having a panel data set allows you to overcome a serious problem in estimation, namely omitted variable bias resulting from unobserved heterogeneity. So what is a panel data set? You have the same observational entity, could be an individual, could be a country, etc., observed at different points in time. So you have at least 2 points in time, right, 1 and 2, or you have whatever, 25 years. Then cap T would be 25. So the correct model is, and now here is the panel data expression, YIT. So you have observation of observational unit I at time t, and you regress it, and although these things have both a cross-sectional and a time series dimension, and also the error term, and this is the unobserved effect. This is something that characterizes individual I or country I, and that doesn't change over time. All right? So it took me a while to produce this, right? But this is what the data set looks like. So you have, this is in fact what the data set we were looking at yesterday and that we're looking at today again looks like. In stacked version, you have the first observational entity with t observations, then you have the second observational entity with t observations, and you go all the way down, and you have, ideally, if it's a so-called balanced panel, you have cap n, cap t observations. N observational units, countries, individuals, and cap t observations per unit. Now, this is a huge matrix of, it's a k plus 1 times nt matrix, right? I mean, if you have a lot of countries and a lot of time periods, then this is a lot of data. These are the parameters that you want to estimate. You want to estimate the constant, and you want to estimate the the coefficients of these regressors. These are the observational, the unobserved effects, which are the same for all time periods, but different across observational units. And this is the error term. Now, remarks: if the regressant and all regressors can be observed for all entities and time periods, the panel is balanced. Secondly, since the data set has both a cross-sectional dimension and a time series dimension, there may be both heteroscedasticity and serial correlation in the error terms. Now, remember, when you have a cross-sectional data set, then you have to decide whether you assume that the error term has the same variance across all observational units. If not, then there's heteroscedasticity. If you have a time series, then you have to assume whether, make an assumption about the correlation of the error term across time. Now here, things are the choice is much bigger, because you have heteroscedasticity, because you have different observational units. Then you have different observations for the same observational unit. So what is the autocorrelation of error terms? Do you make any assumption on that? And finally, you could also assume that errors are correlated across cross-sectional units. And it might actually be that errors might be correlated across cross-sectional units across time. So let me just give you an example at the risk of, suppose you have 2 observation units and you have 2 periods of time, right? And then you have this is the variance covariance matrix. Now, this thing here, this fellow is basically epsilon 1, 1, epsilon 2, epsilon 2, 1, epsilon 2, 2. That has dimension 4 by 4. And it captures, so right, this is basically the variance of this thing. This is the variance of that thing. This is the variance of that thing. This is the variance of that thing. Now, please note, this is the first observational unit. This is the second observational unit. Now, you could make the assumption, that's what we usually do, is that we say this is equal to the same, right? Right? We assume that the error is the same, the variance is the same, no matter whether you observe it at time period 1 or time period 2. But now, homoscedasticity would actually impose that sigma 1 squared is equal to sigma 2 squared. Now, but what the point I want to make is we have all other kinds of correlations to fill, right? We have this one, which is the correlation of 1, 1, 1, 2, right? So is this thing correlated with that thing? Which is, of course, the same thing as saying this is the correlation of 1, 2 with 1, 1. Here we have the correlation of 2, 1, 2, 2. And here we would have the correlation between 2, 2 and 2, 1. Now, these two things are the same. But this is kind of within the observational unit, the correlation across time. And then you have that other stuff, which allows for the possibility that the error terms in the first observational unit are somehow correlated with the error terms in the second observational unit. And then you have to decide at the same point in time or across time. So you have the dimension or the dimension of the covariance matrix for a panel data set is much bigger, and you have much more choices. Good. Now, I'll come back to that because this is an issue that will be relevant when we look at the IMF's estimation. Now, some of the parameters could be individual specific, right? You could allow that the marginal effect of some variable differs across observational units. So you might argue that that the effect of the fiscal balance on the current account balance depends on the country specifics. Now, of course, if you do that, you increase the number of parameters to be estimated big time. You can do that. You couldn't do that in a cross-sectional data set because in the cross-sectional data set, you would essentially have as many parameters to be estimated as observations. But in a panel data set, you still have the time series dimension. But of course, please note, adding parameters to be estimated reduces the precision of the estimate because it reduces n minus k. Good, so I never did that, the last thing. So to compute standard errors, you have to make an assumption about the variance covariance matrix. This is what I just alluded to. Heteroscedasticity across observational units. Do you assume that the variance of the error terms is the same across observational units? If not, then you allow for heteroscedasticity, which is in the panel data. This is usually a good assumption, especially when you have very different countries in the sample, which we have in this EBA regression. Secondly, serial correlation within observational units. So is the realization of the error term in period 1 related to the error term in the same observational unit in period 2? And please note, making these assumptions has two implications. The first one is you might estimate things differently. You probably know the difference between generalized least squares and ordinary least squares. Generalized least squares uses assumptions on the structure of the error terms to estimate more efficiently. Actually, so you run another regression. The alternative is that you do plain and vanilla OLS and that you correct the standard errors, right? The white matrix, or heteroscedasticity consistent matrix, or clustering the standard errors. So you do not estimate differently, but you estimate by OLS, and then you adjust the standard errors, which is important for the t-statistics. Good. Now let me come. Now the fixed effect estimator, treating Ci as a fixed effect, allows it to be correlated with the regressors. Now this is a great thing because you're killing the problem. Killing is not a good word. You're solving the problem, right? But killing is maybe not such a bad word, on the other hand, because it comes at a sacrifice. What the fixed effects estimator does, it implicitly introduces a dummy variable for every observational entity. So, now some people, there's different perspectives on this. Some people actually take this seriously, and they estimate when you estimate a fixed effects regression in eViews, it delivers the estimated fixed effects for each observational unit. So it's basically like you're running this regression and you're estimating this as a country-specific intercept, right? And you're not pulled. It's like you don't know how high it is, and you don't know exactly what it is, but you know that there's something specific. It's like you say for you have YIT on the vertical axis, you have XKIT that's on the horizontal axis, and you would say this is the relationship for country A, and that would be the relationship for country B, right? So you shift, you allow for the intercept to differ. You say there's something determining the dependent variable that's country specific, and it's like a country specific intercept, and that you estimate. So people like eViews says that's the way you do it. A person like Jeff Wooldridge, who has written, I don't know whether you know that textbook by Jeff Wooldridge, Econometrics of Panel Data, you know. Wooldridge says it doesn't make sense. We don't know exactly kind of we cannot do inference on those things, so it doesn't make sense to actually even mention them. What Wooldridge emphasizes is that when you introduce this country-specific constant, what you implicitly do is you transform the variables. And you transform the variables according to the so-called within transformation. Now, the within transformation works as follows. So you have, suppose you have just one regressor, right? Beta 1 IT plus epsilon IT. Oops, that's wrong. I'm missing out on the plus epsilon I. No, it's Ci plus epsilon IT. Good. Now suppose you're computing yi prime, yi dot, which is the mean for this cross-sectional unit for all observations, right? So if suppose you have observations 1, 2, 3, 4, 5, it's 11, right? And you have 5 observations, so it's 11 divided by 5, which is probably 2.2, right? So that would be, and you do the same thing for, and this is of course the same, and then you have this thing. Now what happens if you subtract the second thing from the first thing? It's beta xit minus xi dot plus epsilon it minus epsilon I dot. Now what has happened to the unobserved effect? It has gone. That's the point, right? The within transformation eliminates this. So it solves the problem by basically eliminating unobserved heterogeneity. That's cool, but it's also expensive. Why is it expensive? Well, it's expensive because essentially you're switching off the cross-sectional dimension. So this variable is, if these are countries, is the deviation from the within-country mean. So you do not look at difference between Vietnam and Thailand and Germany, here and there, but you look at differences over time for the data in Vietnam from the Vietnam-specific mean, deviations in Thailand from the Thailand-specific mean, deviations in Germany from the German-specific mean. So you're reducing the data set to the time series. All the variation comes from the time series dimension. And this is, of course, costly because you're throwing away a lot of information. So this is why using the fixed effects estimator is expensive. It's like you have a cold and you're using antibiotics, right? Antibiotics is sometimes the only thing that helps, right? But it's dangerous, right? Because of course you can develop resistance and so on. So if I have a simple cold in Germany, so actually that happened before I came here. I had a pretty tough cold, and I was short of taking antibiotics that I thought, and I actually took them here, just in case, touch wood, but I never used them. So I fortunately drinking a lot of tea and helped. So that's the point. I don't want to. I'm not a medical doctor. I don't want to give you any medical advice. So this is deviation from the mean. Now here's another name for the fixed effects: least squares dummy variable estimator. So there's all kinds of names for the same thing. That's a bit nasty, right? Some people talk about the LSDV estimator. Some people talk about the fixed effects estimator. Some people talk about the within estimator, and the within estimator comes from the fact that this is the within transformation. Okay. So remarks. Within transformation eliminates unobserved heterogeneity. So problem solved. However, for time-invariant regressors, this difference is 0. This is what we had with the regional dummies yesterday, right? I mean, when we run a fixed effects regression and we have regional dummies, no way that we can estimate the effect of belonging to a certain region. Now, the problem is bigger. Sometimes you have variables that matter a lot, but that don't move a lot across time, like demographic variables. We know that demographic variables have an effect on the current account balance, but they don't change very strongly over time, right? They move very slowly. So this difference